And so, we'll now define our third law of thermodynamics. We're going to see that the entropy, S, for a perfect pure crystal at 0 Kelvin will be defined as 0. We have no entropy for a absolutely perfect pure crystal at absolute 0. And so that's important that we define our 0 point, because we were able to say that, for a particular substance, if we're just looking at its entropy in general, everything will have a positive entropy. You cannot have a negative entropy for one substance. You can have a negative entropy delta S for a process that involves multiple substances, but you cannot have a negative S by itself. And in fact, we can't have 0 either. We're going to see, unlike for heats of formation, which we saw that those were equal to 0 for elements in their standard state, for the molar entropy, standard molar entropy for elements, the F got cut off here, for elements in their standard state will not be 0. In Discord, I will link for us a table similar to this one, which will have for us delta H values, delta G values, that's something we'll see next, and S values. Notice for these, there is no delta with S. So these are going to be standard molar entropies. That's our S with the naught symbol up top. So we've seen delta HF before. We use heats of formation before. Note that for the pure substance in its natural elemental state, it's 0. It'll be the same for delta G, as we'll see. That's another one we'll look at later this chapter. But for S, they're always going to be, for normal substances, they should always be positive values. You'll see some negative ones only for things that are ionic. So things that have come from separating an ion from its crystal lattice. So we're not going to worry about those because those don't normally exist in this way. By removing electrons, this is not something that happens spontaneously, right? We would need something to react with it to remove those electrons. So we don't normally see negative S values. So, but that's kind of the only time we would see them. So as you can see, by and large, we're going to see, except for certain ions being formed, all of our delta S's will be positive values. All right, we're not going to see them as 0, of course, because that's defined for a perfect crystal. All right, so remember, again, ions are not things we see by themselves. They're always as part of compounds normally. So, for example, if you're looking at an aluminum ion, you're really seeing it in the aluminum crystal. And so at 25 degrees Celsius, that aluminum chloride has a positive entropy. So we're not going to worry about the ions in this chapter. All right, but this means we have now a way of quantifying delta S. And so we can take our absolute favorite reaction of all time, our absolute favorite, and determine the delta S for this reaction. We looked at the reverse reaction in the previous video, where we looked at ammonia breaking into hydrogen and nitrogen, and that was entropically favorable, right? Let's take a look at what happens when we look at the delta S for this. If we go ahead and evaluate delta S for this reaction, we can do that. We can say, okay, we can, just like before, delta S at standard states would be equal to the S of your products minus the S of your reactants, the sum of those. So just like before with delta H, right, we always did product minus reactants. We're going to do the same thing here. So we're looking at 2 times the S of ammonia minus 3 times the S of hydrogen minus the S of nitrogen. And go ahead and pause the video like I will and look up those numbers on the table. Now that we've looked those up, we can do the math and calculate it to be negative 198.3 joules per Kelvin. Those are the units of entropy, right? So technically the entropy values are joules per mole, but we know that these are standard states. So the coefficient of 2 means 2 moles. Coefficient of 3 means 3 moles. So putting this together, we get this. And so we expected, remember last time, we had a positive entropy when breaking this apart because we're making more gas molecules. But now that we're making fewer in the reverse reaction, we indeed have a negative entropy. So our entropy has gone down. That is to be expected. And so again, this is always related to the system. If we want to establish whether this is a spontaneous process or not, we need to look at the delta S of the universe and apply that second law of thermodynamics, right? Delta S for the surroundings is something a little bit harder to do. We actually have to use some other math here, and without bogging you down with the details, it's simply going to be the negative delta H of your system over the temperature. So just accept that. Accept this as a formula. So the delta S of your surroundings will be the negative delta H over the temperature at constant pressure, technically, which most reactions take place in. And if we do this, we can calculate delta H of the system by looking at delta HFs, right? We can do the same thing for all of this. We can say delta HF of ammonia, 2 of those, minus 3 times the delta HF of hydrogen, which is 0, minus the delta HF of nitrogen, which is also 0. So it's really 2 times delta HF of ammonia, which is going to be equal to, I'll just get it to say now, we have negative 92.38 kilojoules. All right, so that's our delta H for this reaction. We have the delta S and we have the delta H. At standard states, that means 25 Celsius or 298 Kelvin. Let's figure out the delta S of our surroundings here. It will be negative 923.800. Nope, too many zeros. 92380, yeah, joules. Remember, we want joules because delta S has units of joules over 298 Kelvin, joules per Kelvin, right? We do this, we get this should be positive, right? Because our delta S is the negative of the delta H. So negative of this. So it'll be positive 310 joules per Kelvin. And so let's evaluate now the delta S of the universe for our favorite process. Will be equal to the delta S of the surroundings plus the delta S of the system. The delta S of the surroundings we evaluated through looking at the delta H, the amount of heat transferred, and then the delta S system is related to our molar entropies. And we got that as negative 198.3. So 310 minus 198.3 joules per Kelvin. This is some positive number. It's 112 joules per Kelvin, if that's a sig fig there, which is positive. Positive value means spontaneous. Hooray! So even though there is a lower entropy associated with this reaction, we're going from 4 moles of gas to 2 moles of gas, the enthalpy also plays a role in determining the spontaneity of the reaction. And we're not going to have to do this ever again because we're going to make an equation that's much easier for us. And we'll do that in the next video.